in science, a law tells us what is happening. So the law of conservation of mass tells us that the mass before reaction is the same as after the reaction. It's like what's going to happen. A theory tells us why. So the kinetic molecular theory is going to explains why gases behave the way they do. There are 5 what are called tenets. Tenets are just like bullet points. It's not something that you need to memorize like word for word and like know like what the third tenet is. But it is something that you're going to use those words to explain, tell me why, and you're going to kind of like in those essay questions of like the difference between potential and kinetic. This is like vocab stuff. Okay? The first tenet says gases consist of large number of molecules that are in constant random motion. We know that. We draw them like this because it shows that we know that they bounce off of things, and these collisions are what the pressure is. So if that was like a balloon, it would keep it inflated. We know we have gas hands, that they're always just moving. The second one, though, is going to be new news for us. That's the field house, obviously. This is a marble in the middle of the field house. It says the combined volume of all the molecules of the gas is negligible. Negligible means that it doesn't count. We can ignore it. Like we're not going to use it for anything. We're going to pretend it doesn't exist relative to the total volume in which the gas is contained. So if I said, today for a project, we're going to go to the field house and I'm going to ask you to calculate the volume of the field house. Probably you would do some length times width times height thing and figure it out. But if I had a single marble in the middle of the field house, you're not going to take the volume of the whole field house and then be like, oh, we have to subtract away that one marble. Like it's so teeny compared to everything else, like it doesn't matter. It's negligible. That's how gas particles are. They're actually like so far apart and so teeny that they don't count. Okay, so it's like if I had a marble in the field house and the next marble was at the bottom of the pool. That's how far apart they are compared to their size. So we can call them negligible, okay? And number 3 says that the gas particles are moving so fast and they're so far apart that we can ignore, like one of the biggest principles of all chemistry is positive part negative, right? That electrostatic attraction, that they're like little tiny magnets. We can ignore them because of number 1, they're moving so fast, they have Zoomy lines, and number 2, they're so far apart. Nowhere else can we ignore positive, heart, negative. Solids, super important. Liquids, we saw with the solutions and the traction, super important. The only time that we can ignore it, and we haven't really even discussed it, is for gases, okay? So when the music starts, talk about these 1, 2, 3. If all you can do is just like copy what I said, that's okay, but if you can summarize it in your own words and then let somebody else summarize it to you, that'd be best. Okay, ready, go. Okay, and then the last 2 have to do with the temperature that we've kind of already talked about. Number 4 says energy can be transferred between collisions. So that's our red, with a lot of kinetic energy runs into our blue because blue means cold to me. And the energy goes from hot to cold, from high to low, and then it makes a bunch of purples. Okay? This says that you can assume that on average, because it's not going to be exact, some are still going to go fast. Some are going to go slow because they just ran into each other. But on average, everyone is purple. Meaning they all have the same kinetic energy. It's a big assumption because really they don't. Like, they're not all going to be identical. But on average, if we average it out, they would be. That's this one. And then this one is that we already know that if it's at the same temperature, they have the same kinetic energy. Energy is in joules. We do not have a joulemeter. This is like a calculated thing, so it's not like how fast or slow, it's how much energy do they have on average. Okay, just quick remind somebody next to you about red, blue, purple, and what that has to do with temperature. Ready to go. The speed of a molecule, it's called root mean. That's supposed to be like a fancy backward U. Root mean squared speed. You did this in pre-calc. You learned like a bunch of different ways to average something, and root mean squared was something that you did do not, that you remembered or you need to remember it. It's just like a fancy way to average stuff. For us, our equation is going to be the square root of 3 R star. That's a fancy R. It's not a regular 0.08206 R. Times temperature over big M. Fancy R has a different unit, so it has a different number. 8.3145. 3145. And the units have kilograms in them. Joules, kilogram, over Kelvin, mole. Our molar mass needs to be, molar mass, like add it up in there, but it needs to be in kilograms. And it has to do with the unit of a joule. A joule is, this is not exact, it's like a kilogram squared per meter or something, per second or something. So that's how come it has to get converted. Okay, temperature in Kelvin like normal. And we can calculate an average. It has to be an average just because molecules don't all do the exact same thing. We'll do a sample with that. Our molar mass is on the bottom of that equation. It's in the denominator. That means it has an inverse relationship. Inverse relationships I call cheerleading hands. So the lower the molar mass, the higher, the faster the speed. The higher the molar mass, the slower the speed, right? If you math it, if you divide by a smaller number, you're going to end up with a faster speed, okay? The other thing, I think you already know this, higher temperature would mean it's faster too. Sometimes you don't even have to math it. It's just like, choose the one that would have the fastest root mean squared speed. You're just looking for the smallest guy. And if you think about it in your brain eyeballs, don't you think like I see like smaller people as faster than bigger people? Or smaller things as faster than bigger things? Vocab. The difference between effusion and diffusion. Diffusion is just mixing. How fast do they mix? If you look in the picture, it's just showing the molecules bouncing around. That's mixing. Effusion, I think we should make this into a balloon. So make that into a balloon. This makes more sense if it's a balloon. In a balloon, you have a knot here. I'm going to do like just a regular latex balloon that you bought at the dollar store or something. Latex is a big molecule, and in between those molecules is a teeny tiny space because we can't have perfect connections between molecules. We can get pretty close, like obviously close enough that I can't stick my hand through it, but comparatively teeny tiny atoms like helium, that's helium, I know that's hard to see, helium, is small enough to bounce out those holes. So we know molecules see their zooming lines, molecules are zooming, but they're also colliding and bouncing off, right? This is a balloon, so that's creating a pressure, but every once in a while, a helium atom is just going to fall right out one of those spaces in between the molecules, yes? Yes. So that's exactly the story I was going to say. So if you buy, not Mylar. Mylar is different and it doesn't have those spaces between the molecules, which is why they stay insulated a lot longer. But latex, just the molecules like really big and chunky, so you can't like squish it together that well. That's why helium balloons only last a few hours, because they're doing this all the time. They're really small, so they're doing this really, really fast, and they just have a really high probability of falling out a hole, right? Falling out one of those spaces. So you can buy that high float stuff. It just creates a seal on here. It's just like a little seal, so there's less of a chance of the little heliums flying out. So they slowly, like they drop, just because there's less and less helium in there. Okay? So when the music starts, talk about the difference between effusion and diffusion. It's a vocab thing. Smaller things go faster, right? We learned that with our root mean squared velocity. It's in the denominator. It's an inverse relationship also. If you just think about it, it's going to have a faster velocity. That means that it's going to have a greater rate of effusion. You might, probably not, but I'm going to show you just in case, you might have to math this and get like an exact number. For that, we're going to use this equation. Compared two different molecules, 1 to number 2. It's inverse, we know smaller is faster, to the molar mass. Square rooting it because that's what our root mean squared velocity is. Okay? And we're going to do a simple problem of that. I'll show you what that means if you actually do have to math it. Make a T-chart. Real versus ideal. Real gases are like, I'm breathing gas. It's for real. Our lab on Wednesday, you're going to get butane out of a lighter. That's a real gas, like not an ideal situation. Ideal means the ideal gas law, PV equals nRT, gives us the right answer. I plug in my numbers that I got from the data, and it's like, oh, it's perfect. Like, it's good results. The ideal gas law works. But it only works under 2 conditions. The first condition is it has to be at a high temperature. The real gases, our real experiment, has to be at high temperature. That just means it needs to be greater than 273 Kelvin, which is 0 degrees Celsius. So as long as we're above freezing in this room, our ideal, which sometimes it feels like we're not, our ideal gas law is going to work really well, okay? And that's because the molecules have to move fast. If they're too slow, then they start attracting and repelling and the ideal gas law breaks. It won't work. We have to move fast enough to ignore the electrostatic attraction, which is positive part negative. As soon as they start attracting like magnets, the ideal gas law 0.08206 does not work, and we're not going to get good results. That's one. The other thing is it has to be at low pressure. Low pressure means that we're not in like a scuba tank, which we're not. It has to be around 1 atm, which today we're low again. It's cloudy, but we're still pretty close. So we're at 744, which is like 0.98 or something, which is really close to 1 atm. If we have low pressure, that means that our molecules are few and far between. If I have high pressure, I have a gazillion of them stuck in a small space. At low pressure, I don't have, so we can ignore their volume. This has to do with the marble in the field house. As soon as they're too packed in there and we can't ignore the volume, PV equals nRT does not work. Okay, when the music starts, talk to somebody about the only two criteria for PV equals nRT to work. Is this song over with yet? Jeez. Show you how to math this. So we're going to go rate of the hydrogen compared to the rate of the UF6. And it's inverse. Smaller is faster. So we're going to put the molar mass. You can use regular molar mass. You don't have to use kilograms for this one. Only use kilograms for the other one. Of the UF6 on top compared to the hydrogen on bottom. And it's going to give you a ratio. Okay? Uranium's down here. It's 238.03. You add it up. Okay? Plug it in. Push a button.